I don't like this angle today. All right, I'm going to put this over here if it's in somebody's way, sorry. That's better. Now, I put some of Jeffrey's data up on the board. I put his current, his potential difference, and his time for like his very first trial. So what I'm going to do is process that so that I can report the thermal energy absorbed by his water as well as the uncertainty in the thermal energy. So the first thing I would like to do is just get my value for Q. So in this lab, right, we were multiplying the current, the potential difference, and the time together in order to get that value. So I'm just going to do that first. I'm not worrying about my uncertainty yet. So 2.2 amperes times 9.0 volts times 360 seconds. We're actually going to get a pretty large amount of energy. And almost all of you did this part right. So I'm getting like 7,128 joules in terms of significant digits. I would round that to 7,100. I'll just leave it alone right now. So we had only two sets of rules for processing uncertainty. We had one set of rules if we're adding and subtracting. We had a different set of rules if we're multiplying and dividing. So here we're obviously multiplying, and our rule is that we can add the relative uncertainties of these things together, or we can add the percent uncertainties of these things together. Which one am I going to do? Relative or percent? I'm going to do relative because it's less work. It cuts out 2 steps if I do the relative uncertainties. Relative uncertainty is the absolute uncertainty in these things divided by their measurement, divided by their value. So the relative uncertainty in the current would be 0.2 divided by 2.2. The relative uncertainty in the potential difference would be 0.5 divided by 9.0. And then the relative uncertainty in the time would be 2 seconds divided by 360 seconds. So if I add those 3 relative uncertainties together, that will give me the relative uncertainty in the thermal energy. So let me do that. I'm just going to do all 3 of these, at the same time on my calculator. And I get, what do I get? 0.1520 other stuff. Can anybody tell me what percent uncertainty there is then in the thermal energy?
15.
Yeah, 15. We're multiply that by 100, that gives us percent. But if I don't have to do that, so why do extra work if I don't have to? But this does mean that there is 15% uncertainty in this 7,128 joules. I want an absolute uncertainty though. I want to know how many joules more or less than this might my data have. So I need to multiply this 7,128 by the relative uncertainty in order to find that. Right? So I'll take the 0.1520, multiply it by 7,128, and I get a pretty big number, 1,083 joules. However, all right, so let me write that. So plus or minus 1,083 joules. I do need to clean this up because uncertainties should only have one significant digit, right? So I would round this to 1,000. And then I do need to get precision agreement between my uncertainty and the data point associated with that. So 7,000 joules plus or minus 1,000 joules would represent the processed value and its uncertainty. And that's how big I would make my Y error bar. Plus or minus, plus 1,000 joules and then minus 1,000 joules. All right, so that's an example. I mean, we could get more complicated than that. We were just combining 3 terms here. We typically don't combine more than that, but we could. Now the other piece that I wanted to mention was what? That 1,000 joules isn't going to be constant for all of your data, right? For many of you did report the same current and potential difference for every trial, but none of you reported the same time for every trial, right? So I don't know what Jeffrey's final data point was, but it was probably something like 20 minutes. So instead of 360 seconds, we're talking about, what would that be, 12,000 seconds, 1,200 seconds, something like that? Whatever. If this gets multiplied by 10, if all of a sudden we have 4,000 seconds, then the relative uncertainty in this, right, probably gets a little smaller. Even if it doesn't, right? Well, I take that back, it has to. So if this is 4,000, then I'm going to have a smaller relative uncertainty. But, right, if I've been doing this for 4,000 seconds, I'm going to have way more energy. So even if this 15% stays constant, the plus or minus, right, that's still going to get huge. That's going to get really huge, because 15% of 7,000 is only 1,000. 15% of like 40,000 is like 6,000 joules, right? It's not going to stay constant. It's almost never going to be the case that all of your error bars in your graph will be the same size. All right, so let me shut up there. You have an example that you can look back at now if you choose to subscribe to the YouTube page, and you can use that to help you later on. Danielle?
Would you use the process point on the graph then, or would you use the more precise one?
All right, so Danielle's asking, you're asking, should I use the rounded values or the unrounded values? I don't have a good answer for you on that. I think you should use the unrounded values. IB thinks you should use the rounded values. So pick who you like better. Cassie?
So the 1,000 is what you would put on the graph of the error bar.
Correct. Yeah, so the question was the 1,000 is what you base your error bar on? Yes. I mean, you can have Excel do error bars based on percent. So you actually could do it as 15.2%. I would never know like what you did. Well, that's not true. I would know, because that would actually be way more precise than that. You should use the 1,000 to answer your question. Elizabeth?
For the 7,000 joules,
Yes.
isn't that supposed to have two significant
It is supposed to have two significant digits, right? That's why I circled the 1 here. But the uncertainty can only have one significant digit, and I have to have the precision of those the same. So the uncertainty forced me to give less significant digits to my Q. Yeah, Rob?
So when we're actually like writing this out on our data table, how do we neatly do this? Like it's like when you showed us at the beginning of the year where
With
we
your
had
sample calculations or on your actual process
Both.
data table?
well, not really the sample calculation as much, but the process data table.
So how would you write this on your process data table? I would have a column. I think there's two ways you can do it. You could have a column for Q, and then have this whole thing in that one cell. I mean, you'd have to do it as text. 7,000 joules plus or minus 1,000 joules. That's probably the best way to do it. If you don't like that way, then you can have the column for Q, right, 7,000 joules, and then have in the next column uncertainty in Q, right? And then you could have plus or minus 1,000 joules there. I think those are both really good, clean ways to show that. All right, let's move on at this point, right? So I'll post either this one or the one I did yesterday for you guys. And we're going to move right into what I'm going to call our battery mystery. So on the cart there, I have a battery. I have all three of our types of meters. Can we move a bunch closer to that cart, but don't like be at least one step back? Be at least one step back so people can see. All right. So what's the electric potential difference of that battery supposed to be?
6.
Yeah, it's supposed to be like 6 volts, right? All right, Danielle, you are furthest away, so I'm going to ask for you to measure the electric potential difference of the battery using the voltmeter. I've put a red piece of tape on the positive terminal of that battery, so that will help you put the red wire near the red tape. So go ahead and measure the electric potential difference for us. And hopefully it's going to be something in the neighborhood of 6 volts. Use the analog one on the right. Yeah, the one that you're right. No, the one that you're by your right hand. The one by your right hand right there. Yeah.
Okay. And I'm putting positive on one positive.
Yeah, you put the red by the red tape and the black on the other side. Great, and then just tell us what that says.
About 7.
All right, so Danielle's saying about 7. Looks to me like it might be a little bit less. Emily, can you take a look also? Let's get a second opinion. So what is it? 6.0? All right, great. So Danielle, can you just write that on the board, the 6.0? All right, so who's next? Jeffrey, you've moved pretty far away. So now, can you please unattach the voltmeter? Now, what we're going to do is hook up the, you're not going to do this, somebody else will do this. We're going to hook up the ammeter directly to the battery to measure how much current we can get out of it. But I want to make a prediction first with how much current there's going to be. So Jeffrey, what I need you to do is turn on the resistance meter, right? And then hook that up to the 2 wires that are coming out of the ammeter. I want to know exactly how much resistance those 2 wires and the ammeter have combined. It doesn't matter which you hook up to which. Red to red and black to black is fine. Makes no difference. How much resistance are we expecting? 1 ohm, 1,000 ohms, 1,000,000 ohms? A lot. Half an ohm, that's not a lot. 1,000,000 ohms, that would be a lot. What we got, Jeffrey? 0.8? All right, can you write whatever that is on the board, please? So pick a value and just write the resistance on the board for us. If it's fluctuating, whatever, just like give a representative value. Now, as soon as Jeffrey gets that value on the board, we should be able to calculate how much current we should get, once we hook up the ammeter to the battery. So he's going to get that on the board, and I'm going to ask you guys to take 20 seconds, right? Grab your calculators and just calculate for us how much current is going to go through that. How much?
Like 7.
7.5?
No, like 6.97.
6.97, that's it? All right, interesting. Very different prediction from yesterday. All right, get back over here. And Jeffrey, we're sure about that resistance? Can you just do it one more time and make sure? Yesterday we got a significantly smaller resistance. It could be that I have different wires, but let's just check it one more time. And then, all right, now, Nick, you're standing pretty far away, so you're on deck here to do the next thing. All right, so he's confirmed that it's pretty darn close. It's a little bit less. Wait a second, it's going down, down, down. It's going down, down, down. How come? What? No, I don't think so. So we're at 0.67 and decreasing.
Is it like touching?
I think Jeffrey did everything fine. It's actually stabilized now at 0.661. All right, so we need to, and it's going down slightly. What did we say earlier about current? Depends on temperature. Right, so maybe it makes sense that as the wires heat up, the resistance changes. It's not the same trend we see with our filament. Right? We should see the opposite, that the resistance should increase as it heats up. We're seeing the opposite here, but that could be. A filament maybe is not the best representative of an ohmic material. So whatever, 0.65 I think is what we can call the resistance. So can we calculate our new current based on that? And then Nick Lersky, right, when you're ready, go ahead. So what's our new prediction for current? 9 amperes. This meter only goes up to 10 amperes, so I hope that we get we're pretty close to our prediction and we don't fry the ammeter. Uh-oh. Whoa!
9.2.
It actually is very close to our prediction.
Oh no, it's dropping.
Dropping.
Yeah, to like 9.
All right. Well, unfortunately, this didn't work at all. Unfortunately, this didn't work at all. What I was expecting, and I'm really curious what the problem is, I was expecting this current to be significantly different from our prediction.
And now it's going down to 8.
Nah, like